So this is starting chapter 5 of S2, continuous variables hypothesis testing. These final 3 chapters are significant ones, and you'll get quite a few questions based on this. Chapter 5 is about continuous scenarios. Chapter 6 is about discrete scenarios, and chapter 7 is about both of them. And the easiest way to start thinking about hypothesis testing is to think about something we all know about, even though you may not have personal experience, and that's being taken to court. Okay? So if we consider a court trying a defendant, in this country it's really important that we believe the defendant is innocent until proved guilty. The proof must be beyond all reasonable doubt before you can call them guilty. The trial starts off with the judge and the jury assuming that the defendant is innocent. That's how we work in this country. And when you are doing a hypothesis test, which could be, for example, you are testing a claim a manufacturer has that bottles of bottled water contain on average more than 500 millilitres or something like that, you always start off with a statement you are going to assume to be true, and that is called the null hypothesis. So the null hypothesis is assumed to be true, and that's what you start with. That bold bit there, can you write down? It always starts with a null hypothesis, which we refer to as H0, that is 0 down the bottom there, and we always assume that's going to be true, and that's the equivalent in a court case of the defendant being innocent. And if we have a null hypothesis, we've always got to think as well of what they might be guilty of. And what they might be guilty of, that in our stats speak is called the alternative hypothesis, which is assumed to be false to start with, unless we find evidence that it isn't false. So the alternative hypothesis, which we denote H1, is the equivalent of him being guilty. In a court of law, what happens about how you decide whether someone's guilty or not is the evidence is all weighed up. The evidence might be forensic evidence, it might be witness statements, it might be all sorts of things. The evidence that we have all comes from statistical tests and observations. I'm only suggesting you copy down the bold bits there. If you want the rest of it, you can always print it off the KLP later on. Okay? It's chapter 5. So the bold bits are still on the board at the moment. Okay? So, the evidence that we use to decide which hypothesis is true, the null hypothesis or the alternative hypothesis, has to come from the sample of items, whatever that we are looking at. And by assuming the null hypothesis to be true, which is what we said we always do, we assume the null hypothesis true, it's possible to calculate probabilities relating to our test statistics. So for example, if we sampled 10 bottles of water and calculated the mean capacity of the water in those bottles, if the claim by the manufacturer was true, we could work out some probabilities. And this will become far more sensible to you when we actually get stuck into it. And what we'd look at is some sort of critical value, such that the probability of exceeding that small value, if the chance of this, what we have seen happen, is smaller than that, then we say actually they're guilty, because it just couldn't have happened by chance. So what we're saying is 5% is deemed to be statistically significant. So for example, if our bottles of water that we sampled on average had less than 500 in it, and the chance of that happening by chance was less than 5%, then we would say the bloke is not filling his bottles properly. Yeah?
Is that like a stated value that the sample...
Any question will say at what percentage, yeah. It's usually 5%. If it doesn't say, it's 5%. But yeah, it will say in every single question what significance level you'll be using. Okay? If we were going to charge Rob Cornish with murder of Corey for any reason, hopefully we would not want to send Rob to prison when he's an innocent man, and we would want that 5% number to be, or Rob would certainly want that 5% number to be considerably smaller than 5%. If it's a 5%, it basically means if we tried Rob 20 times, because 5% is 1/20th, 1 out of 20 times we'd declare him guilty when actually he isn't. So Rob would want that number there to be far smaller. What Corey would feel about it, we don't really know. So, there's one thing I think that's you've already seen. This one here, this last bullet point here, if you do reject the null hypothesis, that implies you have no alternative but to accept the alternative hypothesis, which sort of makes sense, really, as we go. You either have to accept the null hypothesis or the alternative hypothesis. So there's a 6-step process that we go through, which is on your handout. So on your handout, the first bit where there's a 6-step process, that is going to be a key 6-step process. If you could cut and stick, I will pause the video just to give you time to cut and stick that 6-step process there. So we got this 6-step process. Every question will go through this. Step 2 here goes back to Chelsea's question, decide on a significance level. In reality, that will always be given to you in the question that you are doing. Okay, and this will become clearer as we go through an example. And we're going to start off by doing example 1. So example 1 says, it's known that students joining year 7 have weights that are normally distributed with a mean of 70 and a standard deviation of 7.5. This is where you think, well, how's it known? And it's known because the great god of statistics has told the person who set the question. In real life, it wouldn't be known. But you just got to accept for now that the great god of statistics has just told you that, and just get on with the question. A random sample of 90 students from the latest intake has a mean of 71.6 kilograms. Here's the question. Is there evidence at the 5% significance level that the mean weight of the new intake basically has changed, has deviated from the normal pattern of 70? So you've got a sample, it's more than 70. So does that mean that actually they're not normal 77.5 squared? Or could they just be that and you just pick some of the heavier people in your sample? That's what we're trying to work out. Okay? So I'm going to take the question off the board, but you've got it in front of you. And what we'll go through now is how we would answer that question. So, what was step 1? What was step 1? Can somebody just tell me?
Decide the alternative of the null.
Yeah, decide the alternative of the null hypothesis. Okay, so we always start our question off with a null hypothesis. The null hypothesis, remember, is no one's guilty, nothing's actually changed, nothing bad going on. So a null hypothesis will be that the mean weight of the new intake is still 70 kilograms. Nothing has actually changed. So you'd write it down as a sentence in an A-level question, and then you'd write it down in notation. Well, the mean weight is mu, so we are saying that mu equals 70 kilograms. This year group are not guilty of being fat. Okay, that's a null hypothesis. So the alternative hypothesis, well, looking back at the question, it said, is there significant evidence that the mean weight is more than 70? So there's your alternative hypothesis. The mean weight of the new intake is more than 70 kilograms. That's our sentence. And if we put that in notation, its mu is greater than 70 kilograms. Sometimes this will be a greater than, sometimes it'll be a less than, sometimes it'll just be a not equal to. Is it different in any way whatsoever?
Do you have to mention 5%?
We will do in a minute. That's in step 2 that will come in. So we're still at step 1 at the moment. But this one here, we always need to make one other observation here. We're only interested in a one sort of deviation. The question only said, is it more than 70? Not is it different from 70? And because it's an inequality sign here, greater than, this is what we call a one-tailed test. A one-tailed test. And it's called that because if I sketch a normal distribution curve, under our null hypothesis, it was that mu was 70. We are just interested in, has mu shifted over here? Is it greater than? That's a one-tailed test. If it said, is it just no longer 70, they may be interested in here or here. That would be called a two-tailed test. So we've got a one-tailed test. So if you want to make a note somewhere that if you use that sign or that sign in your alternative hypothesis, it's called a one-tailed test. Or if you used a not equal to sign in your hypothesis, then that will be called a two-tailed test. Well, that is step 1 dealt with. Step 1 was define the null and alternative hypothesis. We've done it in words and we've done it in symbols. So step 2 was decide on a significance level. Well, the decision's been taken for you. Step 2, we were told that we are to use 5% significance level. And that will always be given to you in the question. Step 3, calculate the critical value and critical region. This is what we haven't really talked about yet. And I think for step 3, which is what we're doing here, this is step 3, that was step 2, a sketch is often very helpful. So, if we do a sketch, the null hypothesis says mu equals 70. We are interested in a one-tailed test at 5%. So, put somewhere on here, do some shading in. That shading in is supposed to represent 5% of your area. We mentioned a critical value. Our critical value is going to be a weight called C, where 5% of the weight exceeds C. If this really is distributed, this curve here, if this really is distributed, normal, 7.5 squared, because that's what it says in the null hypothesis. So we start off believing that to be true. So that is believed to start with. That is believed, and that's from the null hypothesis, H0. So what we're going to do in a minute, we're going to work out this critical value C, and if the mean of our sample is in the shaded area here, if a mean of our sample is greater than C, then we are going to conclude they are actually heavier as a year group than averaging 70. Because the chance of our sample just getting those people being that is 5% or less, and we're declaring that's so unlikely that actually the whole year group is actually heavier. If our sample mean is less than that C value, then we're going to conclude no, they're not heavier. Our sample, has not concluded that they are heavier. We could have just got that by chance. So, this C here is going to be our critical value, and we are going to use our test statistic. And the only test statistic we have is the mean of the weights, W. Now we know that the weights are distributed normally 77.5 squared. So what do we know about the distribution of W bar, the mean of those weights?
70 times 90.
Sorry?
70 times 90.
We're not adding them up, so it's not going to be that. Central limit theorem here, this is the sample mean.
77.5 squared.
Yeah, you're going the right way there, Billy, yeah. Remember, this will be mu sigma squared over n. This is where the central limit theorem is coming in. It's the distribution of the sample means. So our W bar is going to be distributed mu, which is 70, sigma squared, which is 7.5 squared, divided by n, how many people were in our sample, and that was 90. So that is the distribution of W bar. And that value over there, if you want to work that out, is 0.625. And what we're going to do now is we're going to find this value of C. We're going to find this critical value C. Sorry? This is... Well, no, not at the moment. We're still in step 3. We're still in step 3 at the moment. We calculate the critical value in the critical region. So we're going to find this critical value C. We always do less than probabilities. So the probability that the weight is less than C, according to our diagram up here, is what? If 5% is on the right, what's to the left of it? 95%, yeah. Okay? So that's where that line there comes from. So turning that into phi notation, it's C minus the mean over the standard deviation that we are dealing with here. We are going to put that equal to our 0.95. So I'm going to have phi of our critical value we don't know. Our mean for W bar is 70. Our sigma squared over n is 0.625, and that needs to be square rooted down there. And I get that 0.95. Is everybody happy what I've done there so far? So we're going back to normal distribution probabilities and phis. So that 70 is that mu, that sigma squared over n is here, and I'm square rooting it. Now if I want to find out the C, what's my next step? Yeah, I need to anti-phi. I need to anti-phi both sides, which means on the left I just get rid of the phi symbol, and on the right I anti-phi 0.95. If you anti-phi 0.95, what do you get? 1.645 is correct. Remember, when you're anti-phiing, these values like 0.95 and common ones at the bottom of the tables, you can use this bit here, you don't have to look in the middle. And you will memorise soon that one there and that one there, because we use them an awful lot. This 0.95 one here is used for one tail tests at 5%. This one here is used for two tail tests at 5%. You'll be using these values an awful lot. You will remember them soon. So that's where that's coming from. So yeah, that one there is 1.645. So you now rearrange that equation to find out what C is. So can you just get your calculators out, rearrange that to find out what C is, our critical value. 71.3, did you say? 77. I've got 71.3 here. Okay. 71.3 should be what we've got. So I'm just going to sketch again that diagram we had earlier. We had mu was 70. We've now worked out 71.3 is where 5% of our probability lies. Okay, and down here we're looking at W bar, the sample means. And we are going, so now in step 3 it said calculate the critical value. Well, the critical value is 71.3. The critical region is the region to the right of that. So our critical region is W bar being greater than 71.3. That's step 3 done. Step 4 is calculate the test statistic. Well, the test statistic was given to us in the question. It said the sample had a mean of 71.6. So if I just move that up there. Moving on to step 4, our test statistic is our sample mean and we were told that in the question that W bar, the mean of the sample weights, was 71.6 kilograms, which is about here somewhere. It's in the critical region. So because this was in the critical region, we can move on to step 5, which is deciding the outcome of the test. What did we say earlier? What did I say earlier? If the sample comes in the critical region, what do we conclude? It's not H0. If it's over here, it's such an extreme value that we're saying they're guilty of being fat. Okay? So we could say, as our test statistic...
Number 5.
Yeah, okay. As our test statistic is in the critical region, that means it's unlikely that it could have occurred by chance.
Can you push up?
Yeah. It's unlikely it could have occurred by chance. I just got to stop the video there because I realise I've run out of time for this clip, and I'll continue another one. So, it's unlikely it could have occurred by chance over there. What we do is we reject H0. So you reject H0 if you're in the tail. And if we reject H0, we have no choice but to accept H1, our alternative hypothesis. So then we can state what our conclusion is. Our conclusion is that the mean weight of the new intake is more than, or is greater than, is more than 70 kilograms. Based on the 5% significance level. So, can everybody see that we've made a decision? That was step 5, and step 6 was state the conclusion in words. So is everybody happy how they can see for that first example, and it will become clear as we do more, that we went through those 6 steps? Okay. I'm just going to pause the video there a minute. Okay, the second example, again, you can cut and stick. This time we've got a machine making bolts. And we know that the bolts coming off this machine are normally distributed, and the diameters are normally distributed with that mean and that variance. How do we know that? The great god of statistics has told the person making the question. Okay, we just don't query that at the moment. After this machine has been serviced, a random sample of 50 bolts is taken to see if the mean diameter has changed. We assume the standard deviation is still the same. The mean of the sample is less than what was up here, and we're now told to see at the 1 significance level whether the mean diameter has changed. So you've all got that question in front of you, so I'm going to take that off the screen. Right, what was step 1 of our 6-step rule?
Write down H0 and H1.
Write down H0 and H1. Yeah, okay. So, what is H0 in this question? H0 is always the status quo, nothing bad has happened. So H0 is...
The mean diameter hasn't changed.
Yeah, the mean diameter hasn't changed, so it's unchanged. Mean diameter, is unchanged and remains at 0.580 centimetres. And in stat speak, in other words, mu equals 0.580 centimetres. So now we are looking at H1. You need to look at the question carefully. What will H1 be?
Mu does not equal 0.
Yeah, it just says test whether it's changed. They're not interested in whether it's got bigger or smaller, they're just interested in whether it's changed. So H1 is the mean diameter has changed So in other words, mu is not 0.580 centimetres. Is this a one-tail or a two-tail test? It's a two-tail test. So at this point I would just do a quick sketch. We are looking at here the diameters. Under the null hypothesis we have 0.580. Two-tail test, so we're going to look at two tails here. A less than tail and a greater than tail. Now, step 2 was the significance level. What significance level are we told to use in this test? Significance level of 1% we were told to use. So that 1% has to be split between these two tails. So that tail there is going to be 0.5%, and that tail there is going to be 0.5%. So that our tails together are their 1%. So in this question we're going to have two critical values to find. One over here, which I'll call C1, and one over here, which I'll call C2. And if the sample's diameter is in one of those tails, we will conclude that H0 is false and we will accept H1. If our sample diameter is in the middle bit, then we'll say it's absolutely fine, we'll accept H0, nothing's changed. Tom?
Would you need to calculate both critical values?
Why are you querying that?
Because we have a statistic that's 0.577, hence it could only be the lower one, not the higher.
You're quite right here, yes, okay. And there was another reason I thought you might be asking. Now, what's another sort of reason?
That they're going to be the same at the top of the sign.
Sorry, it's the...
Because they're equal distance.
Yeah, that's right. There's symmetry involved here as well, yeah. If you know that that is 0.6, which is 0.02 above it, then you know this one's 0.02 below it, and it's 0.56, whatever. So yeah, there's symmetry and things in there you can use. So, step 2 was the significance level, which we said is 1%. We've done our diagram. Step 3, calculate the critical value in the critical region. So, we're on to that step 3 now. Okay. Now, we are going to use the distribution of D bar, and this will be normally distributed, and it's always mu sigma squared over n. Well, from what we're told by the great god of statistics, under the null hypothesis, that mu is 0.58. You always there use mu from the null hypothesis. Okay, it's always mu from the null hypothesis that goes in there. The standard deviation we're given is 0.015, so that's the standard deviation. That's the variance, and we are always dividing by n the size of our sample, which was 50. So that is the distribution we're going to be using for D bar. Yep.
When would you actually ever use this? When was it actually?
For trading standards for quality control purposes is when it would be used. Okay. So, to save you a bit of time, I'll tell you that over here comes down to be... Actually, I can't tell you what that is. I haven't actually worked it out. 4.5 times 10 to the negative 6. Okay, thank you. Right, so Tom's already pointed out that the sample statistic is lower than this mean. So what we are going to do, first of all, is find C1. That critical value on the left is the one that we're interested in. Well, we know that the probability of D bar being less than C1 is going to be 0.5%, which is a decimal, is 0.005. So if we go into our phi notation, it's going to be at C1, our critical value, minus the mean over this sigma squared over n square rooted, which you've already told me is that number up there. And I'm going to put that equal to 0.005. And just like last time, what's the next thing to do once we've reached that stage? Anti-phi, yeah. Which on the left-hand side is just taking away the phi. I got anti-phi 0.005. Now that's where the problem comes. You can't anti-phi that. So can anybody remember, anti-phying a small number, what do we do? Negative anti-phi of 1 minus the small number, yeah. So that's negative anti-phi of 0.995. 0.995 again is in the bottom of that green table. 2.576 is what somebody said, and that's right. So now it's a case of rearranging that equation, that left-hand side and that right-hand side, and you should be able to work out what C1 is. Anybody got?
0.5745.
Yes. Okay. So, what I've done here is just put that on my diagram. I'm going to cover that one up for a minute. We've got our two tails here. As somebody said, by symmetry, you can work out the one on the right. If you work out that gap, if you do 0.580, take away the lower one to work out that gap, and then add that on to the 580, you will get that value there, purely by symmetry. Okay?
How about 0.585? Could I get 0.745?
Which one are you at? That one there, that's...
Yeah, I didn't get that. I got 0.585.
did you square root in the bottom of the thing? Because that is correct.
You did remember the negatives of 5 when you
What did you get, Billy? 5855?
Oh, no, it's not right.
Okay, we've now worked out then our critical regions, okay? Our critical regions are as follows. Our critical regions are if the diameter is less than 0.5745 or if the diameter's mean is greater than 0.5855. If it's in those regions, then we will reject H0. If it's in a critical region, we will reject H0, which means we will have no option but to accept H1. But what was our step for the test statistic? It was given to us. What was the test statistic? 0.577. It was in here, isn't it? The test statistic we were told is 0.577, which is not in the tail. So we will not reject H0, we will accept H0. So step 5, the decision, we will accept H0 because our test statistic was not in the tail, or either tail. The test statistic D bar, which was 0.577, was not in a critical region. And then step 6, of putting it into words. Now I'm going to write this one out slightly more fully because we should really mention the significance level of what we're doing. So we can say that we conclude at the 1% significance level, because if we used a different significance level, we might come up with a different conclusion. But at the 1% significance level, we conclude the mean length is unchanged. i.e. mu is still 0.580 centimetres. Are we happy about that process? So your homework is cut and stick what you need to, including example 3, because that's what we're starting on next lesson. Okay? So we're still looking at hypothesis testing for continuous random variables only. If you think back to last time, we had a 6-point plan, really, of things to go through for every hypothesis test we came across. We had 6 steps that we would go through. So the next example we're going through, example number 3, it says x follows a normal distribution, mean 185, variance 15 squared, and a sample of 25 items is taken, and the sample mean, x bar, is 179. We have to test at the 5% level whether or not the mean has fallen. So basically, do we still believe the population mean is 185, or has the population mean fallen? So what was step 1 of any hypothesis test?
Write down the null.
Write down the null and alternative hypothesis, yeah. So H0 is nothing exciting has happened, it's always just the status quo. So in stats language, mu is still 185, and in English, the mean has not fallen, or the mean is unchanged. Well, here it actually has not fallen. So, after our null hypothesis, we do our alternative hypothesis, H1, and we're told what that is in the question. The mean has fallen. So that is mu is less than 185. The mean has fallen. And also in step 1, although I don't think it was written down as it was in brackets in our bullet point for step 1, what do we also write down at this point, or decide or observe at this point? One or two tail test, yeah. That symbol there tells us this is a one-tailed test. It's a one-tailed test because it's not a not equal to sign, it's a less than sign. So, step 2, decide on the significance level of the test. We are told we are working at a 5% significance level. Step 3, calculate a critical value in a critical region. I think this is a good point always to do a drawing. If you draw your normal curve, under the null hypothesis, our mean is 185. We're doing a 5% one-tail test that it's fallen. So our critical region is going to be to the left of this C value, where this shaded area here is going to be 5%. And we need to find out what this C value is. And then we're going to look at our test statistic, and our test statistic is the 179. If the 179 is where my pen is pointing, which hypothesis will we accept? H1. If my pen... If the test statistic was anywhere over here, we would accept H0. So the next thing we need to do then is work out the test statistic. Well, we're using the distribution of x bar. X bar is normal mu sigma squared over n. That's the distribution of x bar from the central limit theorem. So in this question, we're going to be basing our x bars on 185, because that's what's in the null hypothesis. Sigma squared is 15 squared. We had a sample of 25. So that's our distribution of x bar. And we want to find the value of C. So we want to find the probability that x is less than C is going to be 5%. And then we've been putting that straight into a phi notation. And can anybody tell me what's going to go inside this phi bracket?
C.
C, yep.
C minus 185
Minus the mean, yep.
over square root of 15 squared equals 25.
Yeah, that's right. That is square rooted, put down there. 5%. Okay. And what's the next thing we do then after we've got that written down?
Anti-phi.
Anti-phi, yeah. Which means on the right, on the left-hand side, we just write that down again.
Is that spelled PH? It's spelled TH.
PHI, yeah, phi. And on the right-hand side, I anti-phi 0.95. Now that's anti-phying something small. How do we cope with anti-phying something small?
So 1 minus also.
One minus that. We anti-phi 1 minus that and put a minus in front of it. So we will do minus anti-phi of 0.95. So if you look in your green books, you can look at the row at the bottom of that page, and it will be there because it's one of those common values. Okay, 0.95, 1.645. You'll be remembering that soon. So we're getting here minus 1.645. Is everybody happy with what we've done up to here? Am I going the right speed? Not too fast. Okay, now we rearrange that equation to find out what C is. Now I think Billy's already done this. Billy, what did you work out that C was when you rearranged that?
I think I've done it wrong. No, I haven't. C was 180.065.
That's correct.
Oh.
Okay, that is correct. So that is what our C value is. Our critical value comes out to be that. If you just rearrange that equation, solve that equation, no need to do it now. I'm just reproducing the diagram from earlier. Okay, so our critical value is 180.065, which is what that's supposed to say there. Our critical region is everywhere to the left of that. And our sample mean was 179. So our sample mean at 179 comes in here. That was our test statistic. It's in the tail, which is unlikely to have happened by chance. I mean, we've said there's only a 5% chance of it being in that tail. So we are going to, as we said earlier, reject H0 and accept H1. So, the final bit, writing down our conclusion, you could say in an A-level exam, as X bar is in the critical region, i.e. it's less than 180.065. See. We reject H0, which means we have no choice other than to accept H1, and then you need to give a wordy answer to that. The mean has fallen. If you wanted to give a really proper example, proper answer, in front of the mean has fallen, we would say, using a 5% significance level, a 5% significance level, we will conclude that the mean has fallen, if you want to be really, really precise in your wording. Any questions, comments about that one?
What happens if C is like exactly on the boundary of the critical like that?
Then I don't think that would happen in an A-level question because it's, and you could go either way really. Yeah. Right, I'll stop that video there and we'll move on to another example in another video clip. Okay, here we go. Next example, example 4. It takes on average 21.75 seconds for a lab rat to complete a task. Placed in a different environment, a random sample of 50 times was taken to complete the task. The data was recorded and it was summarised in the figures we have here. The sum of the times and the sum of the squares of the times. Test at the 5% level whether the new environment has changed the mean time to complete the task. Why is this example in my notes? What is different here?
You have to work out. You've got sigma t and sigma t squared.
as opposed to,
Just being given the distribution.
yeah, that's right. We don't have the population parameters here. Okay, so in this example here, we don't have the population mean and variance. So that is the key difference here. What we have instead is we have summary data. So we have summary data from our sample. So, what's the implication of that?
We have to work it out ourselves.
Work what out?
Mu and sigma squared.
Using what technique, process? Unbiased estimators, yeah. So we will need to use unbiased estimators somewhere in this question. Okay. So, that's why this question is in here. So, let's go back to the beginning first of all, and we'll work those things out as we need to go through. So, step one was come up with your hypotheses. So, step one, null hypothesis. Well, let's look at the question. It says, test at the 5% level whether the new environment has changed the mean time. So, the null hypothesis is the mean has not changed. Mu is still 21.75 that we are told. The alternative hypothesis, H1, it says test whether it has changed. So the mean has changed. So what will I write down in stats language for that?
Mu does not equal 21.75.
Yeah, does not equal. It's not a greater than or equal to, it's just has it changed. And as soon as I write my alternative hypothesis down, what else am I usually writing? Well, always writing down at that point. Yeah, this is a two-tail test.
Do you get a mark for that?
We'll look at some mark schemes. We will look at some real A-level questions with some mark schemes. Right, step two. Decide on the significance level of the test. We're told it's 5% significance level that we're using. At this point, this is when I decide I'm going to draw a diagram. Then I can work out sort of where I'm heading and what I'm doing. Under my null hypothesis, mu is 21.75. It's a two-tail test, so I'm interested in tails at either side, and those tails together have got to add up to 5%. So each tail is going to have 2.5% in it, which means I'm going to have two critical values, critical value 1 on the left, critical value 2 on the right. And if my sample statistic, my sample mean is in one of those tails, I will reject H0 and accept H1. If my sample mean is in the white bit in the middle, the clear bit, then I will stick with H0. So, I've got to do my calculation next. So for my calculation, I need to know the distribution that I'm using. So we're talking about time and a sample of time. So what I need now is the distribution of t bar. Normally distributed mu. I don't know what that is, so I'll have to use mu hat. And sigma squared over n. Well, I don't know what sigma squared is, so I have to use sigma hat. Sigma squared hat there as well. Actually, I said one thing there that's incorrect. Sorry? Yeah, under the null hypothesis, we know that mu is 21.75. So yeah, actually don't need to work out mu hat. I am going to work on the basis of that's 21.75 in there, because that's what my null hypothesis says. So actually I don't need mu hat. What I need is sigma squared hat. So can somebody tell me the formula for sigma squared hat, an unbiased estimator of the variance?
N over n minus 1 sigma t squared over n minus sigma q squared.
Yeah, okay. It's n minus n over n minus 1 of the sample variance, and that's what you were telling me. The sample variance is sigma t squared over n minus t bar squared, and that t bar is add up all the t's and divide by how many there are. So in the question we were given sigma t squared, we were given sigma t, we know what n is 50. So if we now work those out, we'll get, substitute into all of those three formulas if you want to do it in steps, we should find out our value for sigma squared hat. So I'm just going to pause the video at this point, see if you can work out sigma squared hat. Okay, so picking up from where we've gone on, we've worked out our value of t bar, worked out our value of s squared, worked out our value of sigma squared hat. So we're going to say now then that t bar is normally distributed. We are accepting the mean from the null hypothesis. And then over here we need sigma squared hat over n. So sigma squared hat over n. That is the distribution of t bar. And now we've got that, we can pretty much proceed as we would with another question, and what we are trying to find now is our critical values. So, which critical value do people want to find first, the C1 or the C2?
C1.
Okay, C1. So if we're going to find C1, we want to find C1, so the probability x bar less than C1 is 2.5%, was a decimal 0.025.
T bar X bar.
T bar, thank you. Thank you. T bar, thank you, Alex. So, phi of C1 minus our mean over that square rooted. I think you're all just doing this on your own now, which is great.
You're supposed to divide by 50. I times by 50.
Yeah, that's sigma squared over n at that point. So doing our trick here, antifying a small number, minus antify one minus it. .96 is a figure that you'll come across, and that again will be ingrained into your brains fairly soon. Two-tail 5% test, it's always 1.96, and you can skip some of these, you'll just know that and can write that down. Then it's rearranging. If anybody's rearranging and can tell me what the C1 is.
21.388.
21.388 is what Chelsea said, that is what I have
Well,
here.
it goes on a little bit longer, but
Okay. So, once you know what C1 is, we can find C2 as well. If I just go back a minute to the diagram, basically if you work out what that gap is there, the distance between those two, and add it onto the mean, we'll get C2. So C2 is equal to mu minus C1, that gap, added on to mu. And if you work that out, you will get C2 as well.
22.11.
Which is, 22.112. So I'm just going to redraw the diagram. So there's the diagram, similar to what we had last time. I've just put the critical values in it. Our sample statistic, T bar, which we worked out a long time ago, T bar was 22.14. 22.14 is there.
When did you work that out?
Okay. We worked that out from T bar was the 1107 divided by 50.
Okay.
We worked that out earlier on. If you look at the board, that's the calculation we had from earlier for T bar. So it's in a tail. So if it's in a tail, we will reject H0, which means we have no option but to accept H1, and then write a wordy conclusion. So we would say at the 5% significance level, we will accept H1, i.e. if we go back to what we said H1 was, that the mean has changed. The mean has changed, which means mu is no longer equal to 21.75 seconds. Now that might be a good thing, or it might be a bad thing. It depends whether a time increasing is a good thing in our study or a bad thing. But that's a conclusion that we've reached about our lab rats in a new environment. Okay, this is the work set so far. Exercise 5A to 5D. Don't go beyond that at the moment, please. Okay, what we're going to do now is go back and look at the examples we've had so far for hypothesis testing, but do one of these alternative approaches and see whether that saves time, whether you prefer it or not. So we're going to look back first of all at example number 1, which I'm summarising here. You've got the full question typed in front of you, hopefully in your notes. But we had a population. What was W? Can anybody tell me what was W in example 1?
I would guess it was
Distributed normally 70 something.
Do we know what W actually stood for?
Weights.
Weights, okay.
Year 7s.
So, weights of year 7, okay, so they're normally distributed, that's what we think, we believe, with a mean of 70 kilograms, a standard deviation of 7.5. We have taken a sample of size 90, and from that sample, the mean weight of our sample was 71.6 kilograms, and we were testing a null hypothesis that mu was still equal to 70 as always, against an alternative hypothesis that the weight had increased and was now greater than 70, and we were doing it at 5%. So that's a summary of example 1 from before, and I suggest you just write those summary details down now.
For the hypothesis, null hypothesis, and
Yep.
alternative hypothesis, can you just write what you've done there?
Well, properly you would do them in words as well, okay, but just to save time now, because we have already written them out in words in the past when we did them the first time round, I'm just not bothering. Okay. So, that is just a summary there of the question. Now, the new approach is we are going to work out Z. Now, we've come across Z's before when we were doing a normal distribution, and our Z here is going to be x bar minus mu over sigma squared over n square rooted, which is not an unfamiliar thing to us. What was the distribution of Z when we were doing the normal distribution before we even did sampling? What was the distribution of Z? Where will you find Zs? I can see something in front of me that contains lots of Zs. Formula book. Yeah, so basic Z is the normal distribution in the formula book, so which has a mean of 0 and a standard deviation and variance of 1. Okay, and that basically then is what's in the formula book, that Z. So, for this question, our Z is going to be sample mean 71.6. Take away our assumed population mean 70. Divided by sigma squared, which is 7.5 squared. Divided by the size of our sample, which is 90, and that is going to be square rooted. It is time to reach for your calculators, press buttons in the right order, and tell me a number.
What's wrong? Guy.
2.0238.
Yeah, I've got 2.02, okay? So that is our Z number. Now, the whole point of this is, if I sketch a normal curve where I'm looking at Z along the bottom, and I have 0 here, because the mean of the Z distribution is 0. This is a one-tailed test I'm doing now, 5% significance level, and I'm interested in, has the weight gone up? So I'm interested in the tail on the right. I'm interested in this 5% over here. Now, from your formula books at the bottom of that page, or possibly even from your memory at this point, because we've come across this number a couple of times before, what is the number that goes along the bottom here for a one-tail 5% test? 1.645 is correct. 1.645. If you can't find that, if I just borrow Chelsea's tables a minute, okay? One tail, 95%. There we go, 95%. That's the number you use for a 5% one tail. 1.645. That's where that came from. Okay. Now, how do we decide on what conclusion to accept here? Are we accepting H0 or not? We say 2.02. Where is that 2.02 on this Z scale? It's over here. That's where 2.02 is, and it's in the critical region. So 2.02 is in the critical region. And what have we previously done if something is in the critical region? Yeah. So we reject H0 and we accept H1, and then we write down some words, which we're not going to bother doing now because we've already done it when we did example 1 before. Job done.
That's a lot of things.
Yeah. Okay.
I look at region if this doesn't work.
No.
Why did one?
Why do you know the
Because sometimes you will need to. I mean,
at the time like other values?
yeah, sometimes you will need to, and you'll need to do that as well for chapter 7, and you'll need the approach as well, sometimes for chapter 6. But this is an easier way of doing it. And there are something which I'm a little bit annoyed about in some ways. It isn't in S2, it's not until S3, confidence intervals. And if any of you go on to do in stats at university as well about confidence intervals, then what we did before would be useful as well. But I'm just going to stop the video at that point. So example 2 was about diameters of bolts, normally distributed, 0.58, was that millimetres or something?
Centimetres.
Centimetres, okay. We had variance, we had a sample of size 50, we were told the sample mean was 0.577. This is all from the old example 2. We were working at a 1% significance level, null hypothesis, alternative hypothesis. So this time this was a two-tailed test. So there's a summary of the example 2. If you look back in your notes, then you've got it sort of written down carefully there. So what I'm going to do now is just sketch my Z curve. 0 here. This is a two-tailed test, so I'm interested in areas, both of these ends. How much area should there be in each of these shaded bits here? Look very carefully at the significance level of this question. Yeah, 1% split into 2, so each of these here is half of a percent, okay, or 0.5%. So just think about that. What then is to the left of that line there? What is totally to the left of that line there as a decimal? 9 something. 995. And that is a number we now need to find then in here. 995. 995. 2.576 it's coming out with. 2.576. So that's at 2.576. And this one over here is at minus 2.576. Those are our critical values. We have shown there our critical regions. And again, this number came from the bottom of the table in the green book, once we'd established what this number here is. So what we have to do now then is to work out our Z value for this test. We said before it's a mean, sample mean, take away the population mean, divided by the sigma squared over root n, or sigma squared over n, or sigma squared over n, all square rooted on the bottom. So, sample mean, 0.577, population mean, 0.58. You can do the rest, some of you may be ahead of me already. Shout out a Z value, somebody, when you've got it.
1.41.
Yep, minus 1.414 I've got written down here. Okay. Where is that on our diagram? It's here somewhere. That's where it is. Okay, that is where minus 1.414 is. Not in a critical region. So, no reason to reject H0. So we will accept H0, and we would write down some words there which explains what that means. You all happy with that one? Good. Stop the video there and we'll move on to example 3 in a minute. The example 3 from last time, can anybody tell me what X was?
Didn't say.
Didn't say, okay. Anyway, it's normally distributed 185, 15 squared. In example 3, we had a sample of 25. We had a sample mean of 179. We were working at the 5% significance level. H0 was mu equals 185, which is the mean from the population. And H1 was that mu is less than 185. So this was a one-tailed test. That's the information we had. So, I would still recommend doing a diagram for all of these questions. It's a one-tail test. We're interested in has it got smaller, so we're interested in just in a tail on the left-hand side. And it's a 5% probability that we want in there. Using the bottom bit of the tables, what number is it here? What's our critical value? It's a 5%.
Minus 1.649.
Yeah, that's right. You're looking at the 95%, the 0.95 decimal on the tables. That will give you 1.645. Because we're on the left of 0, it'll be a negative 1. So that's our critical value. We work out our Z, our sample, minus our mean, over our variance divided by our sample size, that bottom bit square rooted. Somebody's probably worked it out already, or not, but is doing it now. I hear tapping.
-2.
Minus 2. Okay. Minus 2 is here. That's where minus 2 is. In the critical region. So we reject H0 and accept H1. And I'll stop it there. In the next clip we'll have example 4 revisited.
I feel region.
Okay, example 4 was a lab rat question. I think they were put in a new environment and time to do something, and we were asked to work out whether their new environment was having an impact on the time, so whether the time was different or not. So, because it's not equal to there, this is going to be a two-tailed test. We're doing it at 5%. We have a sample mean. We have an unbiased estimator for the population variance, and we worked that out when we did example 4 last time. So, if you were doing this approach, you would still have had to work that out, which we'd worked out last time. It wouldn't just be necessarily given to you. But given we have already worked that out in the past, I'm just going to go straight to my diagram in terms of Z. This is a two-tailed test at 5%, which I think is the most common one you do, really. Two-tail at 5%. And what's the magic number at the bottom for a two-tail 5%?
2.576.
Not for a two-tail 5%. We're looking for 2.5%.
1.696, sir.
1.96, yeah. 2.5% there. So to the left of that line, we are wanting 97.5%. So you're looking in the table at the 0.975 number, and it will come out at 1.96. So two-tail, 5% is 1.96 minus 1.96. You will remember pretty quickly the 1.96 figure and the 1.645 figure. Okay, so there we go. So we need to work out our Z value of our sample mean minus our population mean divided by the standard error of the mean. Shall I tell you what it is to save all the tapping going on? Yeah. 2.114. So who's going to tell me what conclusion do I reach? Yeah, that's right, that's here. Okay, that's where my 2.114 is. It's in the critical region, so I will reject H0 and accept H1. So bear in mind that when you do these things for real, they're not necessarily quite as quick as what we have done now, because we did do some background work when we did this the first time round. Even on things just like reading the question, which takes a bit of time, which we didn't bother doing now, and writing down your hypotheses and things like that, and in this one, working out an unbiased estimator for the population variance. But it is a quicker way of doing it. Okay? So at this point now, you should be able to go through and do everything in question in chapter 5. For the benefit of those who aren't here now, you need to look on the KRP as well, and there is a homework on chapter 5 which has gone out today, which is due in the first day back after half term in the afternoon, and there's also another everything you've done in S2 so far open book test on the KRP, so if you can look at that as well.